How's Ignite going so far? Nah, that didn't sound very exciting. Well, welcome. Today we're here to talk about Windows 10 security internals. How many of you have ever been to one of my sessions before? So quite a lot of you. So this will definitely be internals. We're going to be looking specifically at the implementation details, so no marketing, no fluff, really trying to understand what's going on inside of Windows and all of the strategies and how that comes together, where we are today, and some suggestions of where we're going. So it's really designed to give you a really good, deep, clear understanding of what the heck is going on inside of Windows. Now, before we get started, I figured I'd kind of plug a buddy of mine's book. So my friend Aaron just released... Wow, nothing's happening on the screen up there. Why do I have nothing on my screen? Okay, now we actually have a screen. Bonus. So we just released Troubleshooting with the Windows Sysinternals Tools 2nd edition. And my favorite part of this entire book. So those of you who've never seen Aaron Margosa speak, he talks about the Sysinternals tools quite a lot. Turns out he's actually the person that wrote this book. Mark just takes it and, much like a college professor, puts his name first in slightly larger type and then sends it out the door. They asked me to write the introduction, acting as if I were J.K. Rowling of Harry Potter fame. And I was so happy that I was able to, in the introduction, refer to my friend Aaron as Mark Rusinovich's house elf. So I encourage you to go and check it out and get started. But let's get started talking about Windows, and what I want to kind of focus on are a couple of key security principles that we're trying to implement inside of Windows, right? And what those principles are revolving around. One is an ongoing effort to isolate and containerize applications, components, and subsystems within Windows. And the other is to do a complete shift in the way we treat software. Historically, software was all trusted by default. That's the antivirus model. Hey, everything is good unless you're in this list of all known bad software. It turns out bad guys are pretty good at making brand new bad software. In fact, better at making bad software than we are at making detection to go and find it. The model of everything's good, everything's innocent until proven guilty doesn't work so well, particularly for certain high security scenarios. So how do we start to invert that and trust code because it's proven it's trustworthy and not just because it happens to be code? So let's talk about what we're doing in terms of isolating, containerizing, and really moving the ball forward. So to really get a grip and our heads around everything that's going on in Windows, we do indeed have to go all the way back to everyone's favorite version of Windows, Windows Vista. And in Windows Vista, we first introduced this concept of UAC, everyone's favorite feature. Interesting little side note, which was actually a pretty funny story. A buddy of mine, his name is Chris Corio, he used to work on the UAC team. He was the program manager who designed the initial implementation. And he happened to be at one of the parties that they were giving when Bill was retiring from full-time work at Microsoft. And they said, you know, what are the 3 things you would go back and undo if you were able to go back and change time? And one of those 3 things was UAC. And he's like, come on, I'm right here, man. In the end, right, there's actually a lot of goodness around UAC, and that's what we want to deconstruct. Most people think of UAC as them prompts, as opposed to a compatibility suite of features and an infrastructure that we've been building on top of. Because the world we came from, the XP and before world, was one where all apps were peers. If you're on the machine, all of the other apps are on the machine with you, and you can interact with them, party with them. There's this great big soup of applications, and they can all go together. And the concept of UAC initially said, let's have a less trusted area. Let's really, start to dive down and remove trust from applications. And to kind of show what that is, I am, of course, going to go to a command line, because that's what you do to demonstrate stuff. I'm going to get this one open, and then I'm going to open up another command prompt, but I'm going to run this one as administrator. Who am I /all? And a quick demo tip, you may notice that conveniently one's blue and one's red. That actually has nothing to do with any detection or code or scripts that I've written. I happen to always launch my elevated command prompts from one shortcut. I launch my unelevated ones with window RCMD, a separate shortcut, and I store the separate colors there. So if you're doing demos, it's kind of a hacky way to go ahead and do it. But what we can see comparing the two are some pretty significant differences in my token, even though both are me. Right, so this is just quick refresher stuff. I know a lot of you are like, yeah, I know that I've seen this stuff since 2006, but it is really important that we get this foundational understanding. We start with this notion of, hey, here's a couple different versions of me. They're both me, they both have me as the SID, but one of them says, hey, here's the, for example, the privileges that I have. And a quick and easy definition for privileges, for those of you who are not familiar with sort of Windows internals and what goes on here, the concept of the standard user and the admin you can think of as being standard users can hork all of their own stuff, admins can hork everybody else's stuff. There's a real fundamental difference. A privilege says, I'm going to give you permission to cross that boundary. So if you have that privilege, you can waltz across that boundary and do things that affect the entire machine. So when I look like a standard user, I can do some things that are going to affect other users. For example, I can shut down the computer. When I do that, other users on the computer are probably going to notice. But if I can't ever shut down my computer, I can't get to standard users by default. So that's pretty important. I can change the time zone. This was a really big complaint that I had leveled at me in a hotel lobby once by someone who was very angry about it, and I made the mistake of wearing a shirt that had a Microsoft logo on it. Problem solved, I no longer wear those shirts. But she was traveling, and her time was wrong, and she couldn't fix it, because you can't on XP. It is a system-wide privilege, because it was tied to changing the time. Changing the system time is an admin right, because if I can change the system time, I have a non-repudiability problem. Change the system time, do the bad thing, change it back, that the time that I did the bad thing according to the logs be visibly somewhere else away from the computer, and then be able to deny it. So it's an admin right, but changing the time zone, I ought to be able to do. So we added a privilege. So I've got a handful, but as a full admin, I've got a whole pile of things. Lots more things I can do. And importantly, the one thing I want to focus in on here is I'm going to run at a different level of integrity. So this was the first concept that we introduced into Windows to enhance authorization. Authorization historically was based on who you are. I am Chris Jackson. I'm a member of these groups, so I can get access to these resources. This adds the dimension of trust. I am Chris Jackson, but this process is less trusted. It's sort of like having a valet key and a regular key. You can hand someone the valet key, it doesn't come with all of your permissions. So your unelevated key is a valet key, or your standard user key is one that also is going to run at a different level. Integrity levels come in a limited subset of flavors typically. Technically, the integrity level is a 32-bit number. So there are about 4 billion possible options that you could choose from. We use 4, so there's lots of room to grow. And those 4 are low, medium, high, and system. A low integrity process is very untrusted. It's one that we anticipate bad things are coming from. Medium is a standard user process. High is an admin process. And system is even above admin. That's at the level of the device itself. Typically, system services are running at that level. So this added a whole new dimension to authorization. So now I can do things like, I'm going to use psexec/l and launch Notepad, but I'm going to launch it with low integrity. So if you want to see the integrity, you can actually use the sysinternals tools, go and find the process. Here's Notepad, and I can add the column for integrity level, and in this case, it is in fact low. You can start to see the lows and the mediums. These are different tiers. Now, the way it is configured by default, you have both a level and a policy. Every securable resource, every resource that has a kernel mode representation has a policy affixed to it. Low integrity, no read up, no write up, and no execute up. The default is low with no write up. That's why it's called mandatory integrity control. It protects the integrity of the system, not the privacy of the system. You can still read it. You just can't write to it. So with a low integrity process, I can say test, right? Here's this process, and I'll go ahead and save it and say, okay, where do you want to put this? And let's go ahead and put this in my documents folder, and we'll just call it test.txt. And here's where we learn that error messages are always accurate. They're like, hey, you don't have permission to save it to documents. How about documents? Oh, that's a novel idea. Let me try that. And we could literally do this forever. It'll just keep, I'm fixing it for you, I'm fixing it for you. Because the people who wrote Notepad never imagined that you'd be an idiot enough to launch it with low integrity. What I can do, though, is I can go into the Documents folder, and I'm going to use a tool called Chummel. It's written by my friend Mark Manassi. Just makes it really easy. It's better than writing code. I want to write a whole bunch of code in front of everyone here, and go into, actually I'm going to make one first so I can change the integrity of it. So if I go into the Documents folder, there's nothing here. I'm going to make a new text document, and I'll call it test.txt. And I'm going to Chummel and test.txt, mark it as low integrity. And now that it's marked, this file, which is a securable resource, has a new policy that says this is accessible by an untrusted process, a low integrity process. And then when I try to save it, you want to replace it? Yes, I'm allowed. So I have this basis. I've now gone from everything is the same, everything is equally trusted, to now I have some tiers. Right? I've got untrusted, I've got normal trust, and I can have high trust like admin processes and system processes. I now have some delineation. It's trust-based authorization, a whole new dimension. And we took this idea and moving into everyone's second favorite operating system, Windows 8, we said, let's build a new app model, right? Because the legacy Win32 app model is one where it assumes this inherent trust, right? This app soup everywhere. And so with the new model, we said, let's start with integrity. And we're going to say that all of these things are untrusted. So if I'm going to grab an arbitrary app from an app store, I'm not necessarily going to trust it. I don't want to make it appear to everything else on my device. I'd like to have it isolated. But the problem is then that I'm isolated, but I'm still, if all of my apps are modern apps, right, which, let's face it, it's still going to be a while, right? But eventually, that could be approximating the truth. They're all modern. They're all still going to end up together because low integrity is not enough. So how do we take it to the next step beyond low integrity and say, you know what, I can't just have them all down in a low integrity mess where they're still commingling. I need to find a way to start putting some boundaries between them. So now I can say this app will be by itself and isolated and containerized. And that notion comes in the app container, right? This notion of now I can put something around you that keeps you isolated from everything else. So if I go and I launch a process, right? So here's a little demo application. I'm going to go ahead and launch it. And here it is launched. And I'm going to take a look with, again, Process Explorer, get some details about this process. So it's app container demo, and of course, naturally, it scrolled away. That's helpful. I love that feature. There we go. So I can start to query this and get some details about the process. So in this case, the process is going to have low integrity. Same as other low integrity apps. So if I look at, say, Internet Explorer will run in low integrity mode except for in the local intranet zone or the trusted site zone. So for all other zones, they'll be in low integrity. Alongside this, Office 2010 and later implements what they call protected view. Again, that's low integrity, same concept. So it's down there with there, but it adds something else. It adds in, if I sort it on the flags, a new flag called the app container flag. And the existence of that app container enforces new rules around authorization. Now, because I am in an app container, when I go through and do authorization, I have to meet those rules.
So if I take this application, right, and there's a couple little bits of code, you don't have to read the code, it's okay. I know, how many of you actually are developers in the room? So like maybe 10, 20%, so not a whole lot. It's not too complicated C++ code, which not a lot of people speak anymore. I'm trying to teach my daughters this. She's 6 and not getting it too well, but hopefully that'll change soon. So it's basically code that says write this file in all these different places. You can kind of parse it out even if you don't really speak it. But we're not here to talk about the code. The idea is I'm going to try and write a file into the documents directory. But I'm in an app container. I'm in an app container, and that's going to block me from writing to all kinds of places. So if I go in and try to execute this bit of code, I'm going to say, yep, call the Win32 API to try and write somewhere, and it's going to spit back immediately, hey, we didn't make it. Error 5. 5 is one of those errors. If you see a 5 at the end of an error, it's nearly always access denied, whether it's at the end, whether it's only a 5, right? But 5 is one of those clues to say, oh, you can't do it. Like we could even go in with Process Monitor and look at the access denied and see it there. I can't write there. I can't write there because I'm in an app container. So if you go and download a store app, it's not going to be able to just start spraying stuff all over your documents folder. By design. It gets its own private area to write stuff, and if it wants to share with other apps on your system, it doesn't do by just going right across the boundary and talking to it directly. It'll have to bounce through the cloud or take some other architectural approach. I've isolated it, so it can't write there. Well, let's deconstruct that isolation to really understand the layers that are in there. Now, we just saw that we had, we're trying to create this file from a low privilege notepad, and we're like, oh, that was actually pretty easy to solve. So let's try doing the same solution. So what it's trying to write is sample2.txt. So let's go ahead and make a new text document and call it sample2.txt. And now that we have this thing made, then let's go back in and we'll just change the name. Sample2.txt, successfully changed it. Now it's marked as low. Let's see if that was enough, right? In this case, still not going to be enough. We're still going to be blocking it. Still going to get access denied. So how do you fix that further? Well, let's take a look. We go in and go specifically into the security tab. We're going to go advanced, and we're going to add. Let's see, where's what I want to do. Oh, that's awesome. They've changed that dialogue. I love running beta builds. I'm going to edit, add. That should do. Okay. I just didn't do the right thing. So off of my local device, let's go and find all of the identities that are in here. Now, app containers themselves have a SID. In fact, you can see that if you look. So if we go back into the demo and open up here, that SID is the SID for the app container. This is an identity for the application itself. Now, we had SIDs for services starting in Windows Vista. That's when we introduced that. So services had an identity. This is an identity for an individual app. So I can grant permission just to this SID, or if I really want to cheat, I can also add permissions for all application packages. So if I had something that anything can write to, I can grant that there. So for the sake of going quickly, we'll go ahead and just do that. Otherwise, I have to copy and paste a really large SID and get that to put. I'm going to give it full control because, hey, principle of most privilege. If it might need to give it everything, don't do that in real life. But I'm trying not to spend the entire session granting permissions and doing all the right thing. But if you were doing a real live implementation, you ought to spend the time. But having done that, right, now we've given app containers the ability to write there. Now we're successful. So there's two layers we had to go through, right? From the isolation perspective, I had the layer of I'm in low integrity. I've got a mandatory integrity control get me past. And I had the identity of the app or the fact that it was an app container to get me past that. Those two different layers are the containerization method that we put in place to help protect those applications, or actually more likely to protect Windows itself and your user identity from the applications that may be more or less trustworthy. So that's the concept we have there. Now we've started to build some barriers in between applications. Now where we've taken that, right, and the kind of things we're thinking about are, we take this app container concept, we apply it to all store apps, but we're also doing it as one example of an implementation in Microsoft Edge. Microsoft Edge puts every single process, because it makes a few, it puts those into an app container. So if I go in and take a look, here's Edge, right, and I can see what's happening, and I am a member of an app container. It is a modern app like other modern apps. The other thing that we do with Microsoft Edge on top of that, which is new for the Anniversary Edition, is if I go to a website that has Flash content, CBS, an American television program, television network happens to have that, right, then I can look and see that I have a couple of different processes going, right? So to kind of decipher the Edge process model, we have Edge, which is going to give you the Chrome for the window itself, and Edge CP, which stands for Edge Content Process. And when I start looking at these content processes, one thing I can look at is I can look at let me get the other one open. The command line, how was it launched? And, oh, I don't have the right one here. Does this not have, oh, watch them have moved off of Flash. That would make me really grumpy. There, it's Flash. Okay. BC host. That is what I'm looking for specifically. So the content process that is hosting Flash is a separate command line to launch it. So now if you have Flash content, turns out Flash, not always the best security reputation. I know that's going to come as a shock to some of you, but there have been some bugs. So how do you protect that? And so we said, all right, well, we have this concept. We're already isolating the browser itself from everything else, but it also turns out that I kind of do some important things inside of a browser. So even if you can't reach out and get to the device, I'd kind of rather you weren't able to reach out and get to other aspects of what's going on the site. So we isolated that further and built Flash into its own content process and used something that we call the child app container. So if I look at the app container SID that we have here, this is the app container SID, and compare it, is the other content process. And I've been trying to figure out a more eloquent way to demo this, right? But if we look at, oh, I hit the wrong button. Boom, that one. If we look at how this SID starts out, they start out looking the same and then they diverge, right? And that's, I'm not having a lot of luck. That's how you can tell. These are actually related, and the Flash content process is a child app container. The parent app container has some ability to control that. So we can create it, it can destroy it. If things are getting out of control, it can manipulate that. So now we further isolate and place a boundary around what we're doing in Flash to provide an additional layer of protection. So you're starting to see a trend here, right? We moved from a world that everything began, you know, dogs and cats living together, right? Everyone was all in the same place, and said, all right, let's at least put some striations, some tiers. Within those tiers, let's put some boundaries, and let's continue to build more and more boundaries. All of that happening inside of Windows. So that's foundational. That's one of the things that we've been doing in terms of how do we further isolate and containerize and build that directly into the platform. Now, the other thing that you no doubt have been noticing, because gosh knows we don't shut up about it, right, is how we're continuing to leverage virtualization to provide additional protections. Because historically, again, we come from a model of everything's living together, and if you have any tiers whatsoever, it's here's the apps, here's the platform, here's the kernel, they're all together. If you get admin, you own the whole thing. If you don't get admin, then you're kind of contained into your user space by that definition. That's where we came from. Again, no isolation. How do we start to move that forward? We think about virtualization-based security. So here's what we've built on that so far. If you're familiar with Credential Guard, if you're familiar with Device Guard, what those are is they're leveraging the hypervisor. So we've got client Hyper-V running underneath it and providing that separation between what's happening in Windows that you're looking at and interacting with and what's happening with the service, whether it be a microservice or whether it be an individual application, protected by that virtualization boundary. Now, in Windows, that virtualization boundary is a security boundary. And we're really cautious and really precise about the meaning of that word, right? Because security boundary doesn't mean it is impenetrable. We are way too wise in the ways of the world to ever say that anything is unbreakable, because everything is breakable. A security boundary doesn't mean there's no bugs, because there is no software of significant size that doesn't have bugs. A security boundary is something that we promise to defend at all costs. We will guard this. And if you think about where we're going as a company, this totally makes sense. Because what can't we do if the virtualization boundary isn't a security boundary? We can't make Azure. And if we can't make Azure, that's really bad news for the company, because you may have noticed we're slightly interested in cloud services. So we have to have virtualization be a security boundary. Let's stand behind it. Because the problem with that app container, right, it's really, really good, is that if someone comes in from the top, they get a desktop app running, they can still come in and party and do all they want to, right? It's not, there's no protection from privilege. With a virtualization-based security, even if I am local administrator, even if I am local system, I don't have permission to cross that boundary. I am contained to the system in which I live. So now we can start to see what have we put on the other side of that virtual boundary. The first thing we did was, hey, we've got some really valuable credentials sitting inside of LSAS memory, which if I'm an admin, I can take very, very easily. If I'm very lazy, I just go and download Mimikatz and let it do it for me. It's sitting right there in memory. Let's move it on the other side so I can't get it. Now, does that mean it's impossible to get it? The answer is no, it's not impossible to get it, because by definition, the intent of what you're storing over there is to be broadcast over a network to authenticate to some other device. What you don't want is someone being able to grab it and take it in the pure raw form. You want to have that be constrained into, hey, what's going to come out of there? So again, defense in depth, I need to think about what's happening, but it's taking away the mechanism by which a lot of people were doing it, because Mimikatz has been replicated as PowerShell scripts in addition to the exes and all the other things. I want to reduce that. So let's put that bit of memory, storing my credentials, on the other side of that boundary to protect it. The next thing we looked at from a containerization perspective was, well, I'd like to constrain exactly what you're doing. And this is kind of leading into our next point, which is trusting code by exception. I want to enforce that I'm only going to run certain code. How do I do that? Well, I've got a great technology, right? Used to be called software restriction policies, then it was called App Locker, and now we call it Device Guard. Although technically we now have both, right? Because Device Guard is really just sort of App Locker on steroids that can kind of interact and work side by side with App Locker. One of the things you may have noticed over the tenure of your dealings with Microsoft is that we like to rename stuff. Every now and then, hey, here's a new name for it, just to kind of make it fresh and new. But the concept is all the same. These are going to be the apps that I either blacklist, they can't run, or I whitelist, these are the only ones that can run. Incidentally, we at Microsoft have actually used AppLocker blacklisting to try and block some torrent-based applications and things like that historically. It's something that we use to run our business, right? The fatal flaw in this concept is that if you're an admin, you can turn it off. How do you stop that? Virtualization boundary. Now if I'm an admin, now if I'm local system and I don't like those rules that I'm enforcing, I can't just turn them off. So now I can get much stricter enforcement that even if I gain privilege on the device through whatever thing, right, unless I happen to gain privilege over the hypervisor itself, which is a much smaller surface area, a much harder target to go and get, I can't do that elevation. So I have virtualization-based security. And where we're going with that, we announced at Ignite in North America, we're going to use this for the browser. It's the first app we're going to do. So now, rather than have the browser be in an app container and sitting right there side by side with me and potentially I can get on the machine, we can put the content process for the browser inside of its own micro virtual machine, so that even if you completely hose the browser and tear it down and gain full control of the machine you get control of is a micro VM that only has a browser content process in it and nothing else and none of your digital assets. Now we're really taking that containerization process and taking our toughest containerization and putting it on the most dangerous surface area. Now there's trade-offs, right? That's an extreme level of containerization because there's all kinds of things you do in your browser that you may want to, persist over time, and it's a separate VM, right? So while the final user experience is different, that's kind of what we're working with is, yeah, now you can't like save a picture because you're not on the same VM. You can't save a document. You can't upload a document. It doesn't work for all scenarios, which is why, in the initial implementation, what we've talked about is, yeah, you can turn on for certain sites or maybe turn it off for certain sites or zones or things like that, right? This concept of how do we let you still have a browser do the things you expect while making it secure? But now it can take that container and move it forward. So a really important dimension to what we do is that containerization. The other pivot is moving towards trusting code by exception, right? And we kind of went over this already. Before, we trusted everything until we saw it was a threat. This is the traditional antivirus model. Interestingly, that model is really tough to follow through to its logical conclusion for all kinds of reasons, right? I mean, how many of you would say that antivirus is enough to protect you against today's threats? Right? It really isn't. When you start looking at the numbers, 99% of adversary activity on your devices and everyone else's devices uses tools that are already on the box and would be whitelisted. Once they get shell, they don't need to run their malware anymore. They may need it to get the initial foothold to trigger some initial exploit, but once they're on, party time. I can't go look for bad stuff because there's no bad stuff on there. So I'm really protecting first and foremost against that initial threat, and that's a moving target. Because they don't have to keep writing malware for everything. They just need to write malware to get the initial beachhead. So moving towards having really solid detection methods. We're not going to see it all. We're going to be too late. So instead we need to start moving towards the device guard concept. I'm going to trust code by exception. Now, the historical challenge that I always had with customers that I worked with that wanted to do some concept of, let's whitelist, let's really protect against specific threats and only allow these things to run. The number one mistake that they make is, let's do it for everything. Let's do it for everything doesn't generally tend to work that well, right? And I say this, in my previous role, for those of you who've seen me at the conferences before, right? It's my initial role from 2006 until a couple years ago was that I owned enterprise application compatibility for Windows, right? Let's get all of the stuff that you used on the old ones, get it working on the new one. That's where we started. And in essentially every single migration that I assisted with, it always began with, I wonder what software we have. Now, it's remarkable to me, right? You go into a company, oh, what are you using? Oh, I don't know. I'll have to go ask. But that's where we are, right? People aren't managing their software. They're just like, oh, I know I have some software out there. People go buy their own, particularly if they're admins. Your users may be buying all kinds of things and installing it. So I start with, I don't know what I have, and let's start that out. So if I try to do everything, it doesn't make a lot of sense. So the first bit of advice is pick a scenario and pick a high-value scenario. And we're going to go into all kinds of details on this in a talk I'm giving later on in the week. It's on Friday morning, if I'm not mistaken, talking about securing endpoint devices, where we talk about this iterative approach that says, let's look at, maybe an administrative scenario, maybe a high-value scenario, right? One example of a customer I worked with is that the customer was a credit card processing firm. And they had a user role within their organization where the user role was, I need to troubleshoot if anything goes wrong in our software. And as a result, to troubleshoot, they had visibility into literally everything. Now imagine you're a bad guy who likes credit card numbers. You might rather enjoy having access to a data stream that would have credit card numbers and how much money and to what account should it go to conveniently swap out, ooh, maybe I'll put this to a slightly different account, mine, en masse, right? It would be catastrophic if someone gained access to that device. So they said, let's protect that device, and let's put the toughest protections in there. So challenge number one is people tried to do too much, focus on specific scenarios, we see a lot bigger success. Challenge number two, and this is an industry problem that we need developers to come along for the ride with, is most of these protections work best in conjunction with digital signatures. If your code isn't signed, that's not what we expect. That digital signature is a verification. This has not been tampered with or modified since I got it. It is an identity for the app, it is a guarantee, and we can trust the signature as opposed to generically trusting, one specific iteration, one version of one app. That signature can be trusted everywhere it gets signed, and then obviously I want to defend that signature to the greatest extent. That, incidentally, was a lot of the folks who used other, third-party products rather than app lockers. App locker, really good if everything's digitally signed. If you're using hash-based authentication, I'm going to go with not really good, kind of hard. And that is an extreme euphemism. It was really difficult to do it with just hashes. So moving to that and getting that protection of whitelisting. But if you can't get all the way to whitelisting, another approach that we've been really successful with is to say, you know what? I can't go and whitelist all of the individual apps. What if I used blacklisting on my user-writable areas? Inherent assumption, my users are not local admins to make this workable. If I say, yep, if it's in some place that only an admin can write to, let's go ahead and let them write there. So if I drop it there, whether it be System Center, Altiris, BigFix, whatever admin software I'm using to deposit my files, if the admin put it there, cool, I'll run it. If the user put it there, it isn't going to run. And this actually turns out to be a really effective defense against things like ransomware when they're trying to drop files. There's a couple different variants of how ransomware spreads. Macros have been the one that I've been seeing a lot recently. But from a protection standpoint, this ends up being a really good defense against things like that. So moving towards whitelisting. So that's part of it. Now I want to trust the code at a process level by exception rather than by default. Let's dig a step further, and underneath that, it's like, well, what about inside of memory itself? What can I do in memory to help protect the code within a process is what I trust? Because Device Guard is going to approve DLLs, it's going to approve XEs, right, at the actual entire container level. But what if I manage to inject arbitrary code of my choice into the middle of my process and get the instruction pointer running at this? That's where we start looking at memory protection. So things like data execution prevention. If you've ever looked at, what's happening in a stack, we'll go in and take a look at the stack of a thread. I'm just going to pick one at random. Right, here's a stack. And the stack is going to show you just all of the function calls inside of the program that have been called and the order in which they're going to wind back. If I'm an adversary, if I want to gain control of that, I can redirect the instruction pointer and point it somewhere else and have it run arbitrary code of my choice. So that's what I, as the attacker, want to do. Well, what are some of the things I can do to protect against that? One really effective protection is data execution prevention. It's really simple. When I'm allocating memory, right, in the end, underneath all of the function calls, I'm making a call to virtual alloc to allocate the memory inside of Windows. When I make that call, I've got to specify read, write, and execute. What do I want for each of those bits? If I don't specify execute, and the instruction pointer lands there, will generate an exception and crash your app. Kind of a pretty aggressive way to do it, like, hey, your app is no longer running, but better than running arbitrary code of the attacker's choice. Now, data execution prevention doesn't work with all software. For example, we had a bit of a struggle enabling it inside of the browser. The reason why might be related to the fact that there was a framework called ATL, or the ActiveX template library, that we, Microsoft, produced for you that was not compatible. It would generate code, forget to mark it as executable, and set the instruction pointer there. And you know what people built with the ActiveX template library? Oddly enough, ActiveX controls. Shockingly, hosted inside the browser, so we couldn't enable that. So we started with this process of, all right, how do we get applications that are working? We made it opt-in. You have to opt in order to get it. But what if they didn't opt in? So we released a product that allowed a mechanism to go in and post hoc opt in. Hey, it wasn't compiled this way, but that's cool. We can turn it on now, right? Then do some testing, make sure we don't break it. With most common scenarios, we'll apply it to the browser, and you just verify that you don't have any ActiveX controls that don't work that way. We will apply it to Office. Office has add-ins. The add-ins might not be compatible. Just verify that your add-ins work and rock and roll. That's the reason why we didn't compile it in by default, is that your add-ins might break, and we didn't want to break those. You can apply that after the fact. It was called EMIT, or the Enhanced Mitigation Experience Toolkit. I gave a session at, I think it was 1 or 2, it may have even been Tech Ed, right? But it was at this event, so that we went into the deep, deep details. So if you're interested in EMIT and all of the mitigations, I'd encourage you to go back. Interestingly enough, it was deemed too nerdy for people who weren't Kiwis, so it was never repeated again, but is passed around by lots and lots of people. So Ignite New Zealand or Tech Ed New Zealand, whichever one it was, gets a ton of press because that session is still often watched. Called EMIT, and allowed me to put post hoc mitigations. Well, that's really interesting and really powerful. It does, however, require that you have a little bit of extra software kind of hanging off the side. And we said, that's kind of suboptimal. I don't want to have my users jack some additional software off onto the side. So we actually introduced a new option in Windows 10. This is shipping in the Anniversary Edition, where you can compile them via group policy directly in Windows itself. So no third-party software needed. I'll go ahead and open this up and talk, and while we're at it, we'll talk about it. But here's the option. I can take a handful of the most effective, most powerful mitigations and give me the ability to apply them to any process that I want to. So let's go take a look at the policy real quick. So I go into System, and then Mitigation Options, Process Mitigation Options. I can enable it, pick a process. I'm going to give it a name, and then give it a value. Now, this is quite possibly the easiest to use group policy we've ever created, and that's saying something. Here is the value you put in to configure it. So that little table in the middle with all those numbers, what we're going to enter is a bit mask that indicates either a 1, yes, please, I would like that feature, a 0, no, thank you, please leave that one turned off, or a question mark, I don't care. For all of these options, and curiously enough, we take bit 1, bit 2, and bit 3, that's DEP, ATL funking for DEP, we use that for IE, and structured exception handling mitigations as well, that's bit number 3, and then for whatever reason we skip like 6 bits, and then move on to option D, which is to turn on ASLR, and then we skip another like 8 bits, and then get up to, well, do we want to enable bottom-up ASLR, always on, always off? Really, I cannot explain how it ended up this way. It's pretty hard to use, right? So some of the things we're looking for is, hey, what can we do to take your EMIT policies and translate them into this group policy, or what can we do to educate? But it kind of starts with, here's what you do. It's kind of crazy, but it does work as a method to apply that. And certainly when I'm thinking about building advanced defenses, if I'm building hardened systems to target something, and we'll talk more about the kinds of systems that we want to harden and how to do specific things like privileged access in a session I'm giving tomorrow on the Secure Modern Enterprise, and we'll talk about that. But that can be really effective. So we've added that. And we'll continue to invest in it, tooling-wise, usability-wise, because we've kind of heard that that may not be the easiest group policy we've ever configured, right? And in a world of rampant double negatives, that's a powerful statement. So we have post-compile mitigations to further harden it, right, and something we continue to invest in, both the mitigations themselves and the ability to apply them to software. One of the mitigations that we've built turns out to be incredibly powerful and difficult to understand. So I'm going to try and explain control flow guard to an audience where 80% of you are not developers using assembly language. That is the bar that I have set. But I'm actually convinced we might be able to get there. So let's go ahead and take a look, and I'll show you the application that I'm running and talk about all the things. And in the end, I cannot promise that you will understand assembly language. It is okay if you don't. I really kind of sometimes do. It depends on what's going on. But to understand what the mitigation is doing. So let's go ahead and close that window, and that window, and that window. Too many windows open. And let's get into, I don't need that anymore. This is all the code. Really, really short bit of code. And really, this is the interesting part right here. Here's what we're protecting against. So I've got code, right, an app, and the app has a bunch of functions. And those functions are going to be callable. And in this case, one of the arguments to a function is a pointer to another function. Since it's a pointer, it can potentially be manipulated. So that's what we want to defend against, someone going after a return-oriented programming attack that will replace that address with the address of their choice. That's the protection. So when we compile this, it's going to know, hey, this is potentially an invalid call. Here's a function. It's going to go through and not only generate the code, but it's also going to generate a bitmap of all valid targets that I could ever jump to. So if I ever try to jump somewhere, it's going to be like, hey, is this an okay place to jump? And if the answer is no, it'll crash the process, stop you from running arbitrary code of the attacker's choice. What that looks like I'm going to do CFG enabled. Go ahead and open it up. And unassemble a function. And let's go ahead and bring our other window up. Let's make this a different color so we can tell the difference. Let's make it, I don't know, green. Helps if I can spell. And we'll unassemble just a random function. And we'll notice when we flip back and forth between the two, they're identical. This is exactly the same program, right? The only difference is one's compiled with CFG enabled and the other one is not. Right? So far, like, okay, that's boring and strange. What are you really trying to get at? So let's unassemble another function. CFG demo, bang, indirect call. Here's where the difference comes in. So now I flip and it's like, there's more stuff. So this function starts here and it just does the actual programming. And here, we've added some additional instructions. Right? So before we do our call, we're going to make this call right here. So it's really straightforward. I'm going to call a function that's passed as an argument before I do compiled into my program is another check. Hey, let's go see if that's okay first. Step one. And if it's okay, go ahead and call it. If it's not okay, right, then this function itself is going to cause you to bomb out. So if I actually disassemble that function, I will see that. So we've actually modified the program itself. There's support within Windows as well to make that really fast. This turns out to be an O of 1 operation. So if you sort of dig way, way back, for some of us a long, long time ago, when you're going into school, O of 1 means it is a constant speed. No matter how many arguments, no matter how big the program, it always happens just as fast, and it's very, very fast. That is going to protect all of my calls. You change the argument, I'm going to do a check and say, is this a valid call target? If it's not a valid call target, boom, out the program goes. We're going to go ahead and crash it. So now it's not just trusted code at the XE or DLL level. I'm able to put in better protection, though I ensure that I have just trusted code for what I'm instructing by instruction, by instruction, by instruction. And that really directionally is where we're trying to go inside of Windows, is to really make it so that we have an environment in which you can choose to apply constraints, that you have the right boundaries for the needs you have, so that you can take the scenario of general purpose computing, free for all, have fun, right? It's a consumer device, all the way down to highly specific, highly secured device. Maybe it's being used by my domain administrators, and I want to make sure that I don't ever run arbitrary other code on that device, that I have all those controls in place, that I can have these memory protections. We still have a lot of work to do in terms of adoption of this. So if I look at all of the processes that have Control Flow Guard, by the way, I can see this as an option inside of Process Explorer. It will tell me who has Control Flow Guard enabled. And one of the things that I'll notice is that it kind of tends to be, I'm going to go with Windows enables Control Flow Guard. This is actually new to me. I'm actually now very, very curious if Office apps are doing it. Let's see, did Excel.exe enable it? There's Excel, and well, the click to run has it, but Office doesn't. Even Office hasn't enabled it yet. So an incredibly strong memory protection. We use it in Edge, we use it in IE, we use it in Windows, not yet being adopted. And it's a single click away. You know, if I go into the options, right, I'll show you how hard it is for the world to start enabling this. If I go into the properties and I'll say, all right, let's go and fix this up, and it is in code generation, Control Flow Guard, I would have to change that answer to yes, and I get that feature. So it's still opt-in, still need to make sure it works, but it ends up being a really powerful mitigation. So that, ladies and gentlemen, is kind of a journey, right? We start off with how do we build the trusted platform itself? How do we start to containerize and isolate? How do we move to that world of running trusted code? And in the end, our hope is that we have provided you with a much more secure platform upon which to develop your important solutions and to pick and choose the right components to make your solution as hardened as you can. Thank you very much.